Let's look at an example, which is a sort of pretty famous and classical one. Goes back a lot more than 100 years. And it's the famous needle of Buffon. Buffon was a French naturalist who, for some reason, also decided to play with probability. And look at the following problem. So you have the two-dimensional plane. And on the plane, we draw a bunch of parallel lines. And those parallel lines are separated by a length. And the lines are apart at distance d. And we throw a needle at random, completely at random. And we'll have to give a meaning to what completely at random means. And when we throw a needle, there's two possibilities. Either the needle is going to fall in a way that does not intersect any of the lines, or it's going to fall in a way that it intersects one of the lines. We're taking the needle to be shorter than this distance, so the needle cannot intersect two lines simultaneously. It either intersects zero or it intersects one of the lines. The question is to find the probability that the needle is going to intersect a line. What's the probability of this? Okay, we're going to approach this problem by using our standard four-step procedure. Set up your sample space, describe a probability law on that sample space, identify the event of interest, and then calculate. These four steps basically correspond to these three bullets and then the last equation down here. So first thing is to set up a sample space. We need some variables to describe what happened in the experiment. So what happens in the experiment is that the needle lands somewhere, and where it lands, we can describe this by specifying the location of the center of the needle. And what do we mean by the location of the center? Well, we can take as our variable to be the distance from the center of the needle to the nearest line. Okay. So it tells us the sort of the vertical distance of the center of the needle from the nearest line. The other thing that matters is the orientation of the needle. So we need one more variable, which we take to be the angle that the needle is forming with the lines. We can put the angle here, or you can put it there. I guess it's still the same angle. So we have these two variables that describe what happened in the experiment. And we can take our sample space to be the set of all possible x's and thetas. What are the possible x's? The lines are d apart, so the nearest line is going to be anywhere between 0 and d over 2 away. So that tells us what the possible x's will be. As for theta, it really depends how you define your angle. We're going to define our theta to be the acute angle that's formed between the needle and a line, if you were to extend it. So theta is going to be something between 0 and pi over 2. So I guess these red pieces really correspond to the part of setting up the sample space. Okay, so that's part one. Second part is we need a model. Okay, let's take our model to be that we basically know nothing about how the needle falls. It can fall in any possible way, and all possible ways are equally likely. Now, if you have those parallel lines and you close your eyes completely and throw a needle completely at random, any x should be equally likely. So we describe that situation by saying that x should have a uniform distribution. That is, it should have a constant density over the range of interest. Similarly, if you kind of spin your needle completely at random, any angle should be as likely as any other angle. And we decide to model this situation by saying that theta also has a uniform distribution over the range of interest. So and finally, where we put it should have nothing to do with how much we rotate it. And we capture this mathematically by saying that x is going to be independent by theta. Now, this is going to be our model. I'm not deriving the model from anything. I'm only saying that this sounds like a model that does not assume any knowledge or preference for certain values of x rather than other values of theta. In the absence of any other particular information you might have in your hands, that's the most reasonable model to come up with. So you model the problem that way. So what's the formula for the joint density? It's going to be the product of the densities of x and theta. Why is it the product? This is because we assumed independence. And the density of x, since it's uniform and since it needs to integrate to 1, that density needs to be 2 over d. That's the density of x. And the density of theta needs to be 2 over pi. That's the value for the density of theta, so that the overall probability over this interval ends up being 1. So now we do have our joint density in our hands. The next thing to do is to identify the event of interest. And this is best done in a picture. And there's two possible situations that one could have. Either the needle falls this way, or it falls this way. So how can we tell if one or the other is going to happen? It has to do with whether this interval here is smaller than that or bigger than that. So we are comparing the height of this interval to that interval. This interval here is capital X. This interval here, what is it? This is half of the length of the needle, which is L over 2. To find this height, we take L over 2 and multiply it with the sine of the angle that we have. So the length of this interval up here is L over 2 times sine theta. If this is smaller than x, we don't have, the needle does not intersect the line. If this is bigger than x, then the needle intersects the line. So the event of interest, that the needle intersects the line, is described this way in terms of x and theta. And now that we have the event of interest described mathematically, all that we need to do is to find the probability of this event. We integrate the joint density over the part of x theta space in which this inequality is true. So it's a double integral over the set of all x's and thetas where this is true. The way to do this integral is we fix theta and we integrate for x's that go from 0 up to that number. And theta can be anything between 0 and pi over 2. So the integral over this set is basically this double integral here. We already have a formula for the joint density. It's 4 over pi d, so we put it here. And now, fortunately, this is a pretty easy integral to evaluate. Integral with respect to x, there's nothing in here, so the integral is just the length of the interval over which we're integrating. It's L over 2 sine theta. And then we need to integrate this with respect to theta. We know that the integral of a sine is a negative cosine. You plug in the values for the negative cosine at the two endpoints. I'm sure you can do this integral. And we finally obtained the answer, which is amazingly simple for such a pretty complicated looking problem. It's 2L over pi d. So some people long time ago, after they looked at this answer, they said that maybe that gives us an interesting way where one could estimate the value of pi, for example, experimentally. How do you do that? Fix L and D, the dimensions of the problem, throw 1,000,000 needles on your piece of paper, see how often your needles do intersect the line. That gives you a number for this quantity. You know L and D, so you can use that to infer pi. And there's an apocryphal story about a wounded soldier in a hospital after the American Civil War who actually had heard about this and was spending his time in the hospital throwing needles on pieces of paper. Don't know if it's true or not, but let's do something similar here. So let's look at this diagram. We fixed the dimensions. This is supposed to be our little d, that's supposed to be our little l. We have the formula from the previous slide that P is 2L over pi d. In this instance, we choose d to be twice L, so this number is 1 over pi. So the probability that the needle hits the line is 1 over pi. So I need needles that are 3.1 centimeters long. I couldn't find such needles, but I could find paper clips that are 3.1 centimeters long. So let's start throwing paper clips at random and see how many of them will end up intersecting the lines. So, good. Okay, so out of 8 paper clips, we have exactly 4 that intersected the line. So our estimate for the probability of intersecting the line is 1 over 2, which gives us an estimate for the value of pi, which is 2. Well, I mean, within an engineering approximation, we're in the right ballpark, right? So this might look like a silly way of trying to estimate pi, and it probably is. On the other hand, this kind of methodology is being used especially by physicists and also by statisticians. It's used a lot. When is it used? If you have an integral to calculate, such as this integral, but you're not lucky and your functions are not so simple where you can do your calculations by hand, and maybe the dimensions are larger. Instead of 2 random variables, you have 100 random variables, so it's a 100-fold integral, then there's no way to do that in a computer. But the way that you can actually do it is by generating random samples of your random variables, doing that simulation over and over many times. That is, by interpreting an integral as a probability, you can use simulation to estimate that probability, and that gives you a way of calculating integrals. And physicists do actually use that a lot, as well as statisticians, computer scientists, and so on. It's a so-called Monte Carlo method for evaluating integrals, and it's a basic piece of the toolbox in science these days.